Sorry, so thank you for the introduction. And so today I'm pleased to present you a quick introduction to the core algorithm that makes almost all of modern AI works, namely the backpropagation algorithm. And to do so, I will rely on this founding paper by Rumelhart, Hinton, and John Williams, and Ronald Williams, sorry. So AI is present everywhere nowadays in our lives and even in research. And the beginning of it can be set to the mid of 20th century. First, theoretically, with the work of Alan Turing, who mathematically formalized computation and rigorously described ways of measuring intelligence that are still used today. And in a more practical way, the work of Frank Rosenblatt, who made the first learning machine called the Mark I perceptron, which was able to, for example, classify photo of men and women. And his ideas were based on mimicking what was known at the time of the human brain. In fact, human brain is what we know, the best machine we know for learning. It's very efficient in terms of energy consumption, very fast in terms of data analysis and data prediction too, and pretty accurate, even though it happens that we do some mistakes, but we are still pretty accurate. So human brain has always inspired AI researchers. And I will skim over the history of AI, and the next talk will go into more details. But noticeably, a major step forward has been made in the 80s when the Hopfield network came, and more noticeably when its extension, the Boltzmann machine, was developed and was able to learn pattern quite efficiently with learning rules based on neurology, like Hebbian learning, for example. And since then, more advanced algorithms have been developed. One of the best one we know for now is a neural network, which is an algorithm that is able to do more and more complex tasks from pattern recognition, for example, to sentence prediction, like for ChatGPT, GPT. And nowadays, most of the modern AI rely on this architecture of neural network. So I will present you this particular architecture, and we will see that this algorithm is based on the technique provided by the paper mentioned in the introduction. So the building block of a neural network is a neuron, and more precisely an artificial neuron. So an artificial neuron is a computation unit which takes input and perform two steps of transformation. It first perform a linear transformation that we can see here, the weighted sum, and then a nonlinear transformation, the function f here. And by doing this two-step procedure, we can compute the state of the network, of the neuron, sorry. And this state can then be used by other neurons somewhere else in the network. So this is the building block of a network. And then a network is just a cluster of neurons, of artificial neurons, that can transmit information from one to another. I will explain you now the particular case of a feed-forward neural network, which is the simplest architecture of neural network, but which is still widely used nowadays. And so a feed-forward neural network is a neural network where the artificial neurons are linked as such. So going from an input layer here on the left to an output layer, and from left to right, where information only transit from one layer to another. So we have here the input, the output, and in between what we call the hidden layers. So there is no connection in between the neurons of the same layer. And the way we will use this tool, this algorithm, is first by training it. So we will feed him some training data. So here I take the example of images of animals. And we will tune the parameters of the network for him to learn from the example we give to him. So I will explain you just in a few moments how we will tune those parameters. But so the first step is to train the network, and then we will feed the network with new data it has never seen. It has never seen in his training process, hoping that he will, in the output, give us the answer we want. So here it predicts the dog. And as we will see, this procedure of generalizing from the training data can be quite hard sometimes. And we will see a bit more why in the technical details. So now I will go into the details of how a feed-forward neural network works.
Mehdi,
Yes.
can I just interrupt you real quick? I have
Yeah.
a question from Nicolas, which is related to something you said about
Yeah.
the fact that any given function can be well approximated.
Yeah.
Do you have an idea of in what space this is true?
What space?
Yes. What space of functions, I imagine?
Okay. So this universal approximation theorem has been first proven for multi-layer perceptron, which is a class of neural network which has some nonlinear function and have more than one hidden layer. So we know that in theory, a multi-layer feed-forward neural network with a nonlinear function as simple as a Heaviside step function can approximate well, in theory, any given function. But in theory means we can have a huge amount of neurons or layer. So in practice, it's not always true.
Okay. Yeah, perhaps we can go a little bit further at the end of your presentation. I'll let
Yeah.
you progress. Thanks.
Okay. Okay. So we are here, and I will present you in detail how a feed-forward neural network works. So we have the input space here. For example, the image of animals that, as I shown you before. And we will transform this input space into the output space by first performing, as I already told you, a linear transformation, a weighted sum, and the coefficient of this weighted sum are called the weights and the biases. And once this linear transformation has been done, we will do a nonlinear transformation by choosing a nonlinear function. And here we have lots of choice possible. The most used ones are the sigmoid-like function, like here, or the rectified linear unit here. And once we have done this two-step process, linear transformation parameterized by the weights and biases, and then the nonlinear transform, we have created our first artificial neurons. So just for the notation, X denotes the state of a neuron, W is the weight, the index above in parentheses is the index of the layer. So 0 means the input layer, this is the 0th layer, 1 is the first hidden layer here, and the index below is the index of the neuron in the layer. So here we have created our first neuron in the first hidden layer, but we can do the same by changing the weights. We can create the second neuron of the first hidden layer. And of course, we can continue creating the third one, the fourth neuron, and so on, as many times as we want. And by doing so, we'll construct our full first hidden layer. And once we have done that, nothing stops us from continuing this process. So we can now construct the first neurons of the second hidden layer by changing the weights and biases, and also the nonlinear function. Then the second neurons of the second hidden layer, and so on, and the 10th, 100 neurons, and so on. And as you understood, I think, we can repeat this process as many times as we want to go to the third layer, third hidden layer, fourth, and so on, until we reach the output layer, which can have as many neurons as we want. Here I just put one, but we can have as many as we want. And we construct then the output space of the network. The output space being at first random, because we randomly choose the weights and biases, And we will tune those weights and biases to make the output space as close as possible to the target space, the desired prediction of the network. So just for the vocabulary, the number of layer of hidden layer is referred to the depth of the network. So deep learning refers to neural network which have more than one hidden layer. And the strength of this algorithm is that it's quite easily parameterized. As we can see, the parameters, the weights and biases are easily implemented, but the number of parameters increase very fast. In fact, in this simple architecture I present you, there is already 900 free parameters to tune in order to make the networks do what we want it to do. And so the question now is how to efficiently tune those weights and biases to train the network. And that's where the historical paper comes into play. Because in 1986, Rumelhart, Hinton, and Williams developed a procedure to tune the parameters of such a neural network. As we can see here, this was the early days of neural network. And so just to be a bit more formal and to explain a bit more clear what happens next, the neural network can be thought of as a function which which goes from the input space and the parameter space to the output space. And we will tune the parameters of the parameter space to make the output space as close as possible to the target space. And in this historical paper, they introduced for the first time in this field the concept of error function, which is a way of measuring the distance between the actual prediction of the network and the desired prediction of the network, what I call the target. So in their papers, they introduce this precise cost function, which is now known as a quadratic cost function. But nowadays, other types of error function exist, like the cross entropy or binary cross entropy loss function, for example. And what this step allows us to do is to make the learning process boiling down to now a minimization process. Because in order to reduce the distance between the actual prediction and the desired prediction, we have to minimize this error function. So now we can use the tools of optimization in mathematics. And as we will see, it's quite performant. So here, I just show you a toy example of an error landscape. So we have the error being the cost function of the output of the network and the target. And we see it lives in the parameter space, which here I just put two parameters, but in practice, it can have billions of parameters for ChatGPT, for example. And the goal is if we start somewhere in this parameter space, in this cost function, is to minimize this error, so to go downhill somewhere in a minima, which will be a local minima. We will discuss about this problem a bit later. But so the goal is to minimize this error. And one of the best known solution to do it is the gradient descent, as they explain in the paper. So we will use gradient descent to minimize this error function. And to do that, we will have to they found a way to compute the partial derivative of the error with respect to each weight in the network. And in fact, by doing so, we will compute the gradient, which is a vector that points upwards. And by going in the opposite direction of the gradient, we will have a vector that points downward in the steepest descent direction, and it will converge to a local minima. So now I will present you how gradient descent is performed in this architecture of feed-forward neural network. This is in the paper of 1986. This is the first time this procedure is described for this particular type of architecture. I will show you show you the derivation of the equation in more modern notation, but all this procedure has been explained first in the paper of 1986. And in fact, the difficulty of computing those gradients comes from the fact that we don't have an explicit formula for the output of the network, but only a recursive procedure. If you recall, in the forward pass, I'll show you earlier, we were using the states of the neurons in the nth layer to compute the states of the neurons in the n+1th layer. But we don't have an explicit formula for the output. And so this makes things a bit harder. So I will present you gradient descent in its full glory with all the equation. It will be a bit heavy, but bear with me. It's just to show you that there is no magic tricks or stuff. It's just mathematics. So as I told you, we will go in the opposite direction of the gradient with a step size that we call the learning rate in the AI community. And to calculate this derivative, we will first introduce an intermediate variable called S, which is nothing more than the linear transformation of the feed-forward path. And by applying the chain rule, we can see that the gradient we are interested in is simply proportional to the derivative of the cost function with respect to this new variable S. And by denoting this gradient delta, we can, by once again applying the chain rule quite carefully, arrive to an expression, a recursive expression for this delta. So here, delta at the layer n is computed thanks to the delta at layer n+1. And if we know the delta at the last layer, we can then propagate this delta back into the network. And in fact, that's where the name backpropagation comes from, because if you see now, we are using the delta in the n+1th layer to compute the delta in the nth layer, so in the layer before. So we are back propagating this little delta. Here in the forward pass, if you recall, we were using some nonlinear function, which the choice were up to the user. And here, what comes into play is a derivative of this nonlinear function. So when we are choosing a nonlinear function, we have to think about its derivative and where it's zero, flat, or not non-flat. So this is an art to choose those parameters. And in the end, thanks to this equation, we have a procedure to update the weights here, weights and biases, with the use of this delta term, which is computed in a recursive fashion. Hence, and it has the same form, hence the name backward pass. So this procedure needs to store the state of the network before optimization. As we can see here, the S needs to be stored at each layer. And we have to know exactly the form on the nonlinear function and its derivative. In the conclusion, as we will see, it can be hard to have all those conditions required. But if we have all that, we have now a procedure to update the weights iteratively, each time we present it a new data. Because in fact, if you see here, the error function not only depends on the parameters, but also on the input of the network. So we have to feed the network with lots of data in order to describe well the output space. And each time we feed new data, we can update the weights and biases thanks to this procedure. So if we go back to the toy example I showed you just before, we have now some equations to compute the gradient everywhere we want, as long as the nonlinear function we use are derivable. And to show you it in practice, if we do an optimization process starting from here, for example, and we let the gradient descent perform, we see that, in fact, we go down the hill to this local minima. And to show you how sensitive this learning procedure is to the choice of the user, let's look at another optimization, now starting to a point very, very close to the initial point we had just before. And as we can see, now the procedure has optimized to another minima, which is a bit better. than the first one. And so it shows that this procedure of training is very sensitive to initial conditions. So this is one major drawback, let's say, of backpropagation, is that it's sensitive to the initial condition. And moreover, if we do another optimization here, for example, so we begin here, try to minimize the error function, we see that in this case, we converge to a quite bad local minima. But by changing the step size, the learning rate, as I explained you before, if we start from the same point, but just changing the learning rate, now we see that the algorithm performs way better and finds much better local minima. So this shows that the procedure of gradient descent is very sensitive to the hyperparameters, what are called the hyperparameters, which are all the parameters that are not trained during the training phase, but are up to the user. So there is a learning rate, I shown you, but also the number of neurons per layer, the choice of the nonlinear function, and so on and so on. So this makes the training quite hard. And in fact, the fact that there are no efficient algorithm to optimize those hyperparameters makes AI user struggling quite a lot because we have to tune those hyperparameters by hand. Moreover, as I mentioned earlier, the number of data needed can be can make the training quite hard because such amount of data may not be available, and the quality of the data is hard to measure, especially when we are using data. A neural network that will be used by everyone, like ChatGPT, for example. The quality of the data is a sensible thing to measure and hard to measure. And the fact that optimization takes place in a very, very high dimensional space makes things hard to handle intellectually. So when things do not work, it's hard to say and to understand why things do not work. And it makes the training process very heavy computationally speaking. And for the limitation of backpropagation, back in the day of the paper in 1986, the author were already aware that this local minima issue was in fact an issue because the gradient descent do not guarantee that we will go to a global minimum or at least to a good local minima. Some technique are used to help the network converging to a good local minima, but still there is no guarantee that your architecture will work to generalize well to other data. And as I told you before, the procedure needs to store the state of the network at each layer at each step and to know exactly the nonlinear functions that are used. So that's why some alternative to backpropagation are used, and especially black box optimization algorithm that only rely on the evaluation of the cost function. For example, genetic algorithm or reinforcement learning. Those ones are the algorithms that I study now to implement a neural network in an optical neural network. But those algorithms have their own drawbacks, namely they are really, really slow compared to backpropagation algorithm. So there is a compromise between performance, speed, and stuff. So that's where we're at nowadays. And with that, thank you for your attention and hoping you will have some questions about what I said.
So thank you very much, Mehdi, for this very nice presentation. We're a little bit taken by time, so we don't have a lot of time
Yeah,
for questions. But I noticed Philippe had a question to ask, Philippe Lalanne. Perhaps you can ask your question.
yeah,
Yes, thank you, Mehdi. Very nice presentation. Uh, I find this architecture very simple. I
yeah.
wonder if the brain is as simple. And my, and and my question is the following. I mean, here it's a vector matrix product, okay, that is iterated in I don't know, in time, in fact. Uh, so my question is about synchronism. I mean, do we have such a high synchronism in the brain? or is it asynchronous? And do we lose something with synchronous versus asynchronous, something like that?
Yeah. Yeah. In fact, yeah, the model I present you is really, I would say, it works on the computer. We can perform matrix multiplication quite fast, and there is, as you said, a synchronous way of performing them. And in fact, the brain, I'm not specialized in neuroscience, so I don't know the full details, but I know that in brain, things take some time to be performed, and things are performed in parallel in some areas and some others. So there is, yeah, an asynchronous way of say activating the neurons in our brain. And I know that there are some architecture of neural network that try to mimic this asynchronous way of firing neurons with spiking neurons, for example, and stuff. So there are some other architectures that try to mimic better the brain by, as you said, making thing asynchronous, for example. Yeah.
Thanks.
Okay, thank you. I had a quick question. In the beginning of your presentation, you said that Turing gave some of the initial or fundamental definitions about intelligence. I was wondering, do you know exactly what he said about intelligence?
So one quote on the top of my head I quite liked from him is that, for example, asking if a computer is intelligent or not is quite a misleading question. The question is not about what is intelligent or not, is how we can discriminate between intelligence and not intelligence. And the fact that something is mimicking perfectly, let's say, human brain can suffice to say that it's intelligent because we cannot distinguish it from intelligence. So he has some key arguments. I don't have them on the top of my head right now, but to describe what would be a machine that we will not be able to discriminate from a human, and that's where his famous Turing test uh, come was born, where the game of Turing test of the imitation game was to take some human to make it discuss with a robot or not a robot. The human do not know. And at the end of the discussion, we will ask the first human to tell if he was discussing with a robot or with a human. And this is the imitation game and how we describe intelligence.
Okay. So thank you very much, Mehdi. I think we will now, you can stop your
Yeah.
screen sharing and we will pass to